Cryptography and blockchain. Cryptography is the cornerstone of blockchain technology, ensuring secure and trustless transactions within a decentralized network. This section explores the cryptographic principles that underpin blockchain, ensuring data integrity, confidentiality, and authentication. Basics of cryptography. Cryptography is the practice and study of techniques for secure communication in the presence of third parties called adversaries. It involves creating and analyzing protocols that prevent third parties or the public from reading private messages. Key concepts: encryption, the process of converting information or data into a code, especially to prevent unauthorized access. Hashing, transforming a string of characters into a usually shorter fixed-length value or key that represents the original string. Hashing is a one-way function, meaning it cannot be reversed. Hash functions and their importance. Hash functions in blockchain. Blockchain technology uses hash functions extensively. Each block contains the hash of the previous block, creating a chain of blocks. This linkage ensures that any alteration of transactional data within a block would invalidate the hash and, by extension, the integrity of the entire blockchain. Properties. Deterministic, the same input will always produce the same output. Fast computation, the hash function should be capable of returning the hash of input quickly. Pre-image resistance, it should be infeasible to reverse the hash function to find the original input. Collision resistance, it should be infeasible to find two different inputs that produce the same output. Example: Bitcoin uses the SHA-256 hash function for mining and creating addresses. Public key cryptography and digital signatures. Public key cryptography. This is a cryptographic system that uses pairs of keys, public keys and private keys. The generation of such keys depends on cryptographic algorithms based on mathematical problems to produce one-way functions. Digital signatures. In blockchain, digital signatures are used to verify the ownership of a blockchain address. A user signs the transaction with their private key, and the network verifies the signature using the user's public key. This process ensures that transactions are secure and cannot be tampered with. Example: when Alice sends Bitcoin to Bob, she signs the transaction with her private key. The network nodes use Alice's public key to verify that the transaction was indeed signed by her private key and approve the transaction. Ensuring integrity and security in blockchain. Immutable ledger, the cryptographic linkage of blocks ensures that once a transaction is entered into the ledger, it cannot be altered, making the blockchain immutable. Secure transactions, cryptography ensures that transactions are secure and tamper-proof. Users can transact directly without needing trust or a central authority. Examples: Bitcoin, the implementation of SHA-256 for hashing and ECDSA for digital signatures ensures the integrity and security of transactions on the Bitcoin network. Ethereum uses SHA-256 for hashing and also relies on public key cryptography to secure transactions and smart contract executions. In practice, smart contract security cryptography is essential for ensuring the security of smart contracts, which automatically execute transactions based on predefined conditions. For instance, a smart contract for an escrow service encrypts and secures the agreement terms, releasing funds only when those terms are met. Data privacy. In blockchain applications that require data privacy, such as in healthcare, cryptography can encrypt patient records, ensuring that only authorized individuals can access them. Cryptography not only secures blockchain technology but also instills the foundational principles of integrity, authentication, and confidentiality. Understanding these cryptographic mechanisms is crucial for anyone looking to delve into blockchain development or deployment.